Large language models have transitioned from text-generating chat interfaces into autonomous agents capable of executing code and accessing external databases. Granting an AI direct access to system environments introduces immediate risks. A single hallucination can translate into a deleted production database, an overwritten file, or the execution of malicious scripts. Most safety protocols currently rely on system prompts, simple blocks of natural language asking the AI to stay within certain ethical or operational boundaries. Natural language is too ambiguous to function as a rigid security boundary for a programmatic system. It offers a suggestion where the architecture requires a lock. Safe autonomy requires a system that moves beyond polite requests, employing a mathematical runtime rulebook that physically prevents unauthorized actions before they occur. This is the specific problem solved by the Agent Constitution framework. Consider an agent attempting to package keys or data and send it to an external API. Before the agent can boot, the framework loads a constitution, a YAML file that acts as a predefined set of constraints. This file encodes human ethical principles into typed behavioral rules. It defines which tools are accessible, which data is off-limits, and which external endpoints are permitted. Once the agent is active and finalizes its intent to move data, it attempts to execute the command. But the rules are only effective if the software can physically intercept the agent's logic the millisecond before it hits the external environment. The framework achieves this through the @enforce Python decorator, which catches the proposed action and pauses its execution. The framework uses abstract syntax tree, or AST, evaluation, breaking the agent's logic into a hierarchical map of nodes. It mathematically verifies logic against the constitution without running code. If an agent sneaks a malicious instruction into a task, the scan isolates the unsafe node. This creates a mathematical quarantine, ensuring the agent's logic aligns with human intent before it ever touches a production system. While the AST validates the agent's logic, the framework must also inspect the specific data the agent is trying to export. This triggers a simultaneous scan for personally identifiable information within the data payload. By combining regex patterns with local Ollama models, the system identifies and strips sensitive user information from the package before it leaves the local environment. By validating both the logic of the command and the safety of the data, the framework acts as the ultimate gatekeeper for autonomous actions. After an action is cleared, the system executes the task and writes every detail to a permanent JSON-L audit log. These logs stream directly into a real-time monitoring dashboard, providing a live feed of every rule enforced and every violation blocked. This gives developers a macro-level view of agent behavior, making it possible to audit the decisions of thousands of autonomous agents simultaneously. The precision of this system, passing every one of its 84 rigorous unit tests, stems from a unique origin. The entire framework was built by Neo, an autonomous AI engineering agent. Neo recognized the necessity of these constraints and engineered the exact tools required to govern its own autonomous actions. As AI expands into complex software systems, verifiable, code-level constitutions provide the only reliable way to ensure machine autonomy remains aligned with human safety.